Hi Chemistry, Mrs. KJ here with 3.05 buffers and titration. Sometimes it is necessary to control the pH of a solution or determine its exact concentration. The pH of a solution is a tricky thing. There are times when the pH needs to be maintained at a constant value. There are other times when you are not sure of the exact concentration of solution and need to know that value. This lesson examines how you do these things by using buffers and titration. Goals for the lesson: explain how buffers stabilize pH, define titration, explain the use of a classical titration apparatus. So pH can be stabilized by buffers, pH can be determined by titration, which uses indicators, and titration is based on neutralization reactions. And you can go to slide 2 to get your study guide, student guide. And from the student guide, I copied down the beginning as well as the keywords and pronunciation. A buffer is any substance in solution that resists pH change by stabilizing hydrogen ion concentration. A buffer neutralizes added acid or base. So really, it keeps the pH the same. Then we have phenolphthalein, which is an indicator, and we'll talk a little bit more about that one later. And we have titration, a lab procedure to deliver a measured volume of solution. And of course, what is it used for? To determine the pH. So we'll add that to our notes and then go back to our reading. There are many cases in which the pH of a substance needs to be controlled. The pH of human blood needs to be between 7.35 and 7.45. Anything higher or lower than that can be dangerous and create harmful complications or even death. Blood is just one example of a substance whose pH needs to be stabilized within a narrow range. The pH of a solution can be stabilized by the addition of a buffer. A buffer is typically a mixture of an acid and a base. When an acid or a base is added to the solution, the buffer will release or absorb hydrogen ions, which act to keep the pH of a solution constant. In many cases, a buffer is a mixture of acids and their conjugate bases. For example, acetic acid, when mixed with its conjugate base of acetate, act as a buffer. So let's look at that in a formula. So we have acetic acid, which is HC2H3O2, plus water. And when you see the double arrow, that means it can turn into this. And it also means that these products can turn back into the original reactants. So it goes back and forth. So you notice that the acetic acid gets rid of its hydrogen and gives it to the water, which makes it a hydronium ion. And then it becomes the conjugate base, acetate. So remember from before, conjugate bases or conjugate acids are whatever the acid or base was before. So for this example, we have an acid. So what it becomes is the conjugate base. In a reaction like this, the extent to which the reaction proceeds determines the pH of the solution. Conjugate base. Consider the reaction where NH3 and H2O are reactants and in equilibrium with NH4O positive and OH negative. Okay, so on the left-hand side of the equation, we have this. On the right-hand side of the equation, we have that, and they can go back and forth. In this reaction, NH3 is the base, and NH4O plus is its conjugate acid. So we had a base, and it turned into this. So we had a base, it turned into its conjugate acid. Water is technically the acid, and OH is its conjugate base, because the water turned into OH negative. Here, we can see that the water turned into a hydronium ion. Which means in this case, since the acetic acid was the obvious acid, water was acting as a base, and therefore it turned into hydronium ion, which would be its conjugate acid. So I added this paragraph to my notes and underlined the key points. Blood, pH needs to be stabilized within a narrow range with the addition of a buffer, a mixture of an acid and a base, and the buffer will release or absorb hydrogen ions, which act to keep the pH of a solution constant. Blood is a solution that must have a tightly controlled pH. Human blood is a complex mixture. The liquid portion of blood, called plasma, is a solution that must maintain a slightly basic pH of about 7.4 for blood to remain healthy. You may have noticed that blood is slightly slippery, and you probably recall that slipperiness is one of the characteristics of bases. I want to pause for a second. When they say the liquid part of blood is plasma, that's not the same kind of plasma we talk about when we talk about phases of matter. When we say solid, liquid, gas, plasma, that kind of plasma is enlightening. It's super highly charged material, and it's very rare on Earth. It is enlightening. It's in the stars, obviously the sun. This kind of plasma is just a liquid. It's very different. The pH of blood is more likely to become acidic as metabolic processes generate acid. Excess amounts of acid in the blood can result in more acid than the body can handle, which can be fatal. Excess amounts of base in the blood can also be fatal. It is essential that plasma contain a buffering system, and it does. Blood is a complex solution whose pH must be narrowly and accurately controlled. There is a buffer that controls the pH of blood. In the human body, the pH of blood is partially controlled by a buffer of carbonic acid, H2CO3, and bicarbonate, HCO3 with a -1 charge. If the blood experiences an increase in acid or base concentration, the equilibrium of this reaction shifts. That is to say, this system, which is more complex than shown here, is a buffer, one that acts to keep the blood pH at about 7.4. So the carbonic acid can turn into hydrogen ion plus bicarbonate, or bicarbonate and hydrogen ion can turn back into carbonic acid. This is a reaction that helps control the pH of human blood. So I added the pH of blood is partially controlled by a buffer of carbonic acid and bicarbonate. If the blood experiences an increase in acid or base concentration, the equilibrium of this reaction shifts to keep the pH constant. This is the biggest mistake people make. They say to keep the pH neutral. Well, neutral is 7. You don't always want it to be neutral. Blood wants to be about 7.4, which is a base. Even though slightly, it's still important. And so the pH needs to be kept constant by a buffer. Titration is a process that allows you to determine the pH of an unknown solution. This is a classic titration setup. It consists of a solution whose pH, hence its H plus, H3O plus concentration, is known. Below the burette is a flask containing the solution whose pH is unknown. All right, so this is the burette. I'm kind of sad they didn't show you the whole thing. It's this long tube. It's about 2 feet long, and it looks like a graduated cylinder in that it measures out milliliters. And then you turn this nozzle right here, and it allows it to drip 1 drop at a time. So you know the pH of the solution in the burette, and you drop it 1 at a time into the flask. And the flask has a substance with an unknown concentration in it, or an unknown pH in it. The flask also contains an indicator. An indicator is a substance that changes color at a certain pH. Phenolphthalein is a common indicator that is clear in acids and turns pink in bases. So if you look at this, right now, is the solution in the flask an acid or a base? It is a base because you can see the color pink. During a titration, the standard solution, the known one or the one up in the burette, is slowly added to the unknown solution. The acid in one solution will neutralize the base in the other. A color change in the solution will indicate that you have just barely exceeded the neutralization point. So up in our definition of phenolphthalein, I added indicator that is clear in acid and turns pink in bases. Perform a titration to determine the concentration of the solution. You add the known chemical very slowly and monitor the pH of the resulting solution. You often phrase this as titrating solution 1 with solution 2. This means that solution 1 is the unknown that is in the flask. The titrant, or solution 2 in the burette, is the standard solution whose pH is known. Try this in the titration activity. The molarity of the sodium hydroxide in the burette is 0.01 molar, or moles per liter. You will add it to the flask containing 80 milliliters of hydrochloric acid whose pH is unknown. When the solution in the flask turns barely pink, you have reached the neutralization point. All right, so we're going to add the sodium hydroxide to the beaker to neutralize the hydrochloric acid solution. The solution is neutral when the color turns and remains pink. So also inside this beaker is phenolphthalein. So we're going to open the valve and you allow it to drop. Now what they're not showing you, which I wish they were, is that the level in the burette goes down, and that's how you can tell how many milliliters you added. And if you can see, look how it's turning pink and then it's turning clear again and then stop. And now it stayed pink. That's how we know it's done. So when you do this for real in a lab, you'll get a little bit of pink and you have to swirl it or mix it around and then it turns clear. And then you add one more drop, swirl it, it turns clear. And then you add one more drop and it turns pink and that's it. It stays pink completely because it's officially a base. The graph shows how the pH of a solution changed. The pH of the unknown solution was low at first. You expected this because it was acidic hydrochloric acid solution. As you added the base, the pH of the solution gradually increased. Then, suddenly, the pH rose quickly. As you went from 12 milliliters to 20 milliliters of added sodium hydroxide solution, the pH rose all the way from about 3 to about 12. After that, the pH stayed near 12. The sharp rise in pH happened when about 16 milliliters of base had been added. The pH at which this sharp rise occurs is called the equivalence point. This is the point at which the solution in the flask is a neutral solution. Any base that is added will quickly cause the solution to be basic, and the indicator will turn pink to let you know. So that's where I was saying that, how you could see that, oh, it was like a little bit pink, and then it went away, a little bit pink, and then it went away, a little bit pink, and it went away, and then boom, it was pink and it stayed pink. And it's kind of interesting how the pH is like slowly, yep, and then it stays constant again. So I added titration to our notes. During a titration, the standard solution, the known one, is slowly added from the burette to the unknown solution in the flask. The acid in one solution will neutralize the base in the other. A color change in the solution will indicate that you have just barely exceeded the neutralization point. And then I just copied the second slide down because, well, it's just well written and you need the graph anyways. So again, when you do your notes, make sure that you add what you feel is best for you. Now you are ready to calculate the concentration of the substance. Recall that you had an acid of unknown concentration and added 0.01 molar sodium hydroxide. At the equivalence point, you know that the total number of moles of sodium hydroxide must equal the total number of moles of hydrochloric acid because the balanced chemical equation indicates that they react with each other in a 1-to-1 ratio and it's neutral. Because you know the molar concentration of sodium hydroxide is 0.01 molar, and the volume you added is 0.016 liters or 16 milliliters, you know how many moles of sodium hydroxide you have added. So calculate the concentration of hydrochloric acid solution from the titration. So first of all, you have to find the moles of sodium hydroxide. Find the number of moles of sodium hydroxide you titrated from the burette. You know the molarity of the sodium hydroxide is 0.01 molar. You know molar stands for moles per liter. You use 16 milliliters of sodium hydroxide to reach the equivalence point. So 0.01 molar is, remember it's moles per liter, but moles per 0.016 liters is going to give you the fact that you have 0.00016 moles of sodium hydroxide. That's how many moles you put in from the burette. Then find moles of hydrochloric acid. Here's your chemical equation. Because the coefficients are both 1 in the balanced equation, you know you have a mole ratio 1-to-1. You know there must have been 0.00016 moles of hydrochloric acid, because that's how many moles of sodium hydroxide we had, in the solution to begin with. Using the mole ratio to find the number of moles of base, so it's a 1-to-1 ratio, therefore the moles at the equivalence point has to equal the moles of the HCl. Because you know the volume of HCl is 80 milliliters, you now can calculate the concentration. So there are 80 milliliters in the flask. So the concentration of HCl, you have how many moles you have divided by